Hello everyone, my name is Michael Horn. This is the third video, part C of one big problem that we've been working on over the past couple videos. And in this one, I will label it part C. I will be showing you guys how to derive a time-dependent material and energy balance equation off the CSTR described. It's kind of being covered by my screen here. I'll move this real quick. By that table right there, and we will then code solve and plot this time-dependent concentration and temperature profiles from the CSTR with the specifics given. So let's get into it. So let's get started with drawing our actual system. We first will have this tank with a mixer in the center with a liquid in there. Now we are going to assume that there is a flow going in. This flow is going to have a concentration in. There's going to be a concentration in the tank, and as it leaves, we are going to assume that this is the same concentration. There's also a temperature going in and a temperature in the tank. Now the second part of this is that there's going to be something called a jacket around this tank. And in this jacket there's going to be a temperature. And out of this source we're also going to assume that this temperature is the same. So I made a couple mistakes here. I'm going to fix them really quick. So this T, that's a big eraser. This T was incorrect, this T is incorrect, and okay, sorry. So this is a flow, not temperature. There's a Q going in, and this temperature in, and then there is a temperature out, and this temperature is changing because it's exothermic. It is an exothermic reaction. And then also in here, the last important part is that this liquid inside has a height. So now that we have the diagram drawn, we can start to derive our equation. So next we are going to find our reaction rate, which is going to be our first equation, K is equal to K naught exponent. And then in these parentheses we're going to have all capitals E over RT at TC, temperature cooling. Now we are going to have to modify this equation and plug in some different types of things so we are actually able to input this into Colab, and that's where we will start to go from here. So as you can see here, I wrote moles with the volume and the concentration written below it. So we are going to try to find this concentration because there's a concentration flowing into the tank, and we're going to assume, like I said before, the concentration flowing out is the same as in. So this is going to change with respect to time. So we're going to add d dt. And the way that we are going to find this is by setting this equal to q in times c a in minus c a. Now the final part of this equation is going to be adding in this section right here. We are going to multiply this K value times the volume and the concentration. Now this total equation here, that I will move this up a little bit. This is our total material balance. I will square this out. So now we have completed our material balance equation and we are able to move from there. So like the material balance, we are going to start out the energy balance equation with the same thing, VC. That's what we're going to start with. Now, this will be relating temperature to energy, so all of the things in the right-hand side that we're going to get to are going to be related to the temperature. And now this VC, you'll notice, is in the wrong units. We need to get this in units of seconds time, so we are going to multiply by the density and temperature. And like I said, it is related to time. So, we're not asking Siri. Release this temperature, sorry. dt over dt. So now this is the left-hand side of the equation. Now we move to the right side. So the first element of this right side of the equation is going to be the Q in in relation to the temperature, Tc minus T. Next we'll have our overall heat of reaction, which is going to be UA times Tn minus T. And finally, the last element is going to be the, since it's exothermic, sorry, there should be a minus, the heat of reaction multiplied by this right there, VKCA. My apologies, I realized I flipped these. These are go over here. And you guys can come over here. Oh, I'm just going to rewrite it. T, C minus T, T, N minus T. Now, we have our energy balance, and we have our material balance. So now that we've successfully derived our two material and energy balance equations, we will be able to move into Google Colaboratory, in which we will take both of these equations, we will substitute them in using NumPy and other arithmetic libraries that we can put into Google Colaboratory, and I'll move this. That little table in between us, we will be using this along with the temperature increase to 305 starting at T equals 0. And we will code, solve, and plot this time-dependent concentration and temperature profiles. So as you can see, I have moved into Google Colab. I have left these two equations that I'm shaking below me right there, just so you guys are aware of what we are working with. And as you can see, there's already a pasted-in library that was provided by our professor that is going to allow us access to the information that we need. And so the first thing that I'm going to need to do, which will take me a little bit of time, is I'm going to have to go in and plug in all of the variables from the problem statement. So let's walk through that. All of these we will label as parameters, so we know what we're working with. The first is Q, and that is equal to 100 units liters per minute. Next is concentration, CAI, which will be equal to 1 mole per liter. Next is temperature in, which will be equal, we'll do Tn, 10 man. Anyway, 350 degrees Kelvin, uppercase K. Next is our volume is going to be 100 liters. Nice simple numbers will make this a lot easier. Would make it a lot easier if you were doing it by hand, which obviously we are not. Next, our density is 100 grams per 1,000 grams per liter. I always forget that number sign. Now, capital C, we are going to equal to 0.239 per gram Kelvin. And then our negative, we'll do NHR, negative heat of reaction, is equal to 5, 1, 2, 3, 4, so 50,000 joules per mole. Only got 6 more, so. All right, our ER is equal to 8,750 degrees Kelvin. Now, our K naught, which we referenced before, is in the equation along with K and all of E and R and T. That is going to be equal to, that's a lot of numbers. Let's make sure I get this right. 72 along with 9 zeros. And that is in minutes negative. And then UA Sorry, this is taking a minute. This is times 4. 1, 2, 3, 4. And that is joules per minute. Kelvin. TC. So TC naught is equal to 300 Kelvin. CA naught is 0.5 moles per liter. And our final one, after all this work, T naught is equal to 350 degrees Kelvin. So now after we did all that hard work of inputting all this, just a few more steps, and then co-laboratory will do the simulations for us. So now we have lots of, I want this to go away. Thank you. We have lots of equations to put in. First, we're going to have to define, just like we did in these, we're going to have to define right-hand side, T, VC. Now, we don't have heights anymore. We are going to have variables like K equals K naught. And we're getting these equations from the material and energy balance equations. We're going to multiply this by NP dot ext negative ER divided by T. Our next equation will be related to the concentration. So dCA is equal to Q Cn minus Ca. That will be divided by volume. And then that subtract away from K times Ca. Next would be our time. So dt. And this is a little bit of a longer equation. Now this is goes along with our energy balance equation because, as you can see, the energy is relating temperature to time, and this equation is relating to temperature, so we're going to use variables in that equation to find this equation. So we're going to start with Q, and we're going to multiply that by Tn minus the original temperature. Then we're going to subtract that variable we listed above, UA, which is 50,000 joules, which will be multiplied by T minus Tc, which will then be divided by rho times V times C. From here, we will add, let's space this out, negative heat of reaction times K value. Is this capital K? Did I make this K? No. Times Ca, which will then be divided by rho times C. And then we still need to return our values, and the values that we need returned are and dt. All right. So now we have to input our tendencies, which I forgot to do originally in the first or the second video, but I'm not going to forget this time. So our tendency, we are going to start off with 10, and we still have to do our t-plot. And this t-plot is going to be equal to np dot ln space, and we're going to start at 0 like usual. We're going to, second will be our tend, and then we're not only going to want 10 spaces here, so we could do about 500. And then next is this long solution equation, which is going to be res equals sp dot integrate. This is always the hardest part to remember all this. Solve underscore IVP. And then here we're going to put right hand side, because that's what we're solving for. 0, tend, close parentheses, comma. And now we're going to go Ca naught, T naught. And our method has been the same for the past couple videos, which we're going to reuse reduce method equals redo underscore output equals true. All right, so now I'm going to make sure there are no errors and come back once we are ready to make the plot. I do want to point out, I did only have one error in this code. The first time we ran it, I realized I accidentally had ext instead of exp, which is not a function instead of numpy. So that was a simple error that was picked up, and now we are ready to begin the plotting process. So now, if you've been following along with any of the other videos, we are going to make a scatter plot. So it's going to be very similar to this, skeleton of what making a subplot is, but we're going to have to make a few changes. So let's bring this over. And we will add a new line of code. Now we'll explain again. So fig equals make subplots. That's going to make us the plot here. But this time we are going to need rows and columns. We're going to need more than just one. So rows we're going to need 2. And then columns we're going to need 1. No, I'm sorry. I have that flipped. Rows are going to need 1. Columns are going to need 2. Now also y this time is not going to obviously equal h1 because we're not worried about heights. This is going to equal CA plot. Mode, mode, 1 second. Okay, I was right. We don't need a mode here. We need name is going to be CA, and then rows, row equals 1, column equals 1. And there's going to be one more line here, because so let's see if this will actually do it for us. T-plot, T, that is exactly what we need. Close that. And then, let me double check. Now let's bring over, let's think about how we want to plot this for a second. So before I went and make the plot, I tried to make sure all errors were taken care of. I did run into one error. I accidentally double defined CA plot, so it was just continuously looping over and over, and it was giving me these really funky graphs and a million errors. So it took me some time to figure out what was wrong. You can see here I highlighted in green what I did. I extracted it from the solution. This was with the help of Gemini. It took me a minute. I was very, very confused. We were able to work through that. The graphs I was getting were not similar to the ones we got in class, so they are fixed. So we'll show you guys what happens now when I run it. 2 beautiful looking pretty graphs in red and blue. Now, you could be asking, what does that mean? I'll tell you. The left is the concentration, as you can see CA over time. So as time goes on, the concentration is getting higher and higher and higher, closer to 1. The temperature is getting lower and lower and lower and lower with time. So now the final portion of this problem is seeing what happens when we increase this temperature here from 300 to 305. Let's run it. Now, these large oscillations will start to occur, and the reason is because it is an exothermic reaction which is highly unstable. So just by increasing this temperature a very, very minute amount in 5 degrees, you're seeing that this concentration dips super fast, and then due to the increase in temperature it has enough to restart. Boom, up, down, up, down, up, down. This is due to the instability of the reaction. The same goes with the temperature. But it starts low, spikes to the top, runs out, goes back to the bottom, and then again has an excess amount, so it's able to restart the reaction and it goes to the top again. So ideally in these situations you want to have a stable temperature that you can find to avoid this instability in the graphs. So thank you for following along, and I hope this was easy to understand and follow. Thanks.